Hello and welcome. This is me, Shamiul Shanto, and this presentation covers my recent coursework for operating system. Now, the task was to install, configure, and evaluate Open vSwitch, a production graduate or virtual switch inside a virtualized environment and using Oracle. Hello and welcome. This is me, Shamiul Shanto, and this presentation covers my recent coursework for operating system. Now, the task was to install, configure, and evaluate Open vSwitch, a production graduate or virtual switch inside a virtualized environment and using Oracle. So here is the agenda for today's presentation. So we have seen sections to cover. Uh, we have 7 sections to cover. We began with the domain of the knowledge, where I explain the theory behind virtualizations and Open vSwitch. Then we move into the practical implementation, setting up the environment, installing OVS, configuring the virtual network, and connecting two virtual machines together. The second half of the presentations focus on evaluations, monitoring system resources under ideal and load conditions. The running control performance test for throughput, latency, and scalability. We finish with the conclusion and recommendations. Let us begin with the domain of knowledge. So these slides introduce the theory of the virtualizations that underpins the entire project. A hypervisor of software that creates and manage virtual machines. There are two types. Type 1 is hypervisors run directly on physical hardware and include product like a VMware XSI and Microsoft Hyper-V. Type 2 hypervisors, on the other hand, sit on the top of an existing operating system. In this project, I used Oracle VirtualBox 7.2.6, and which is a type of hypervisor running on a Windows 11 host. The guest virtual machine runs Divine, um, GNU or Linux 13, allocated with the virtual CPUs, 2 gigabytes of RAM and 20 gigabytes of virtual disk storage. Um, Visualizations demonstrates several core operating systems concepts. Process isolations is achieved through Linux kernel, namespace, CPU, and memory are um, dynamically allocated by the hypervisor scheduler, and network is abstract using virtual Ethernet pairs of software bridges. The architecture diagram on the left shows how all these layers sit on top of the physical hardware. Well, Open vSwitch or OVS is a production quality multiplayer virtual switch released under the Apache 2.0 license. It was specifically designed for automated environments and software-defined networking, where virtual switches need to be controlled programmatically. In this project, I used Open vSwitch version 3.5.0 installed from the Divine package repository. The OVS has three main components. The first is OVS VS Switch, and the main daemon that runs in user space is implements all the virtual switch logic. The second is OVS DV server, which provides a database or interface for strong switch configurations persistently, so your bridge and port definitions survive a reboot. The third component is the kernel data path, which provides first path packet forwarding inside the Linux kernel of performance. From an operating system perspective, OBS demonstrate the interplay between user space and kernel space. The daemon communicates with the kernel module using netlinks sockets, and the kernel handles the actual packet forwarding at high speed, while the daemon handles the control plane decisions. Well, this slide explains the virtual networking concepts that we implemented. A physical and Ethernet switch forwards frames at layer 2 using dedicated hardware chips at line rate. A virtual switch that does the same thing in software, which makes it far from flexible. You can add ports, define flow rules, and integrate with orchestration systems, but it is bounded by the CPU resources of the most of the host machine. The key abstractions we used in this project are Linux network namespace, which give each virtual host a completely isolated network state, its own routing table interfaces, and firewall rules. Virtual Ethernet pairs or bed pairs which work like a pipe. Traffic Etherning, one end comes out the other, and the OVS bridge, which is the virtual switch connecting everything together. The topology diagram on the right shows exactly how this is wired. Namespace one at address 192.168.100.2 connects all through a vet pair into the OVS bridge called OVS Bro. On the other side, a second vet pair connects to the namespace 2 at address 192.168.100.3. This gives us an isolated virtual network eternally within the Devane BM, which we can then test with the P and iPerf3. So now we move from theory into practice. These sections cover how I set up the entire environment from scratch, creating the virtual machine, installing Divine, and the building and configuring Open vSwitch. Each step is supported by screenshot captured directly from the virtual machine, showing the username Shanto29 to confirm the work was done by me. So let's start. So yeah, for the environment setup, I downloaded Oracle VirtualBox 7.2.6 and the the Divine 13 Truxil and 64 ISO. I created a new virtual machine with two virtual CPUs, 2 gigabytes of RAM, and 20 gigabytes BDI disk. Two network adapters were configured. The first for the internet access and the second for the simulating inter-VM communication later. So the figure on the left confirms the BM hardware configuration inside VirtualBox. The figure on the right shows Divine fully installed and booted with the unnamed command confirming the kernel version 6.12. During setup, I created the user account Shanto29 as required by the brief. I also added the user to the sudo group by logging in as a root and running user mode. This was necessary because the user was not initially in the sudoers file. So in the next one, installing Open vSwitch on Debian was straightforward. Using the adapter package manager, I ran a apt-get update followed by an apt-get installed Open vSwitch switch which pulled in OBS version 3.5.0 along with all its dependencies, and I then enabled and start the service using systematically, which ensures OVS start automatically at boot. To verify the installations, I ran three commands: OVS vesticle show, which confirmed that daemon was connected to the database; OVS vextel and dash dash version, which displays version 3.5.0, and systematical status, which confirm both the switch daemon and database server were active and running. The screenshot on the left captures all of the output with the username Shanto29 visible in the prompt, confirming the work and was performed under the correct account. At this point, OVS was fully operational and ready for network configuration. In the next one, with the OVS installed, the next step was to build a virtual network. I followed a series of configurations commands. First I was created an OVS bridge called OVS Bro, using the OVS best add bar. Then I created two virtual Ethernet pairs, VET0 paired with the VET0 OVS and the VET1 paired with the VET1 OVS. I created two Linux network namespace NS1 and NS2 to simulate the separate host. The VET0 interface was moved into NS1 and the VET1 into NS2, while the other ends VET0 and OVS and the VET1 OVS were added as ports to the OVS bridge, and then I assigned IP address namespace and got 192.168.102, and the namespace 2 got 192.168.100.3, both on a 24 subnet. All interfaces were brought up with IP links to set up the figure, and the left shows the full bridge and the interface configurations. The figure on the right shows the connectivity test. I ran a ping from NS1 to NS2. And as you can see, we achieved 0% packet loss with the consistent response time in the sub milliseconds range. This confirms the obvious bridge is correctly forwarding traffic between the two namespace. Okay. So as an extension to the core task, I also configured a multi-noded virtual switching scenario. This involved setting up a second domain virtual machine and interconnecting the two BMs through and their OVS instance. Each BM runs its own OVS bridge. To connect them, I used an overlay tunnel. Open vSwitch supports GRE and VXLAN tunnel types, which encapsulate the virtual switch traffic over the existing IP network between the two BMS. The topology diagram on the slide illustrates how BM1 and BM2 each have their own obvious bridge connector namespace, and the tunnel port links two bridges together. This means traffic from the namespace on BM1 and transparently reach a namespace on BM2 as if they were on the same physical switch. This is exactly how OpenStack and the Kubernetes networking works in production. OVS bridge on each compute node are connected by the VXLAN tunnel, creating a virtual overlay network that spans their entire cluster. This extension demonstrates the real-world scalability of Open vSwitch beyond a single machine. So we now move on to the evaluation systems, evaluation section, so which accounts for 40% of the total mark. 24 resource monitoring and 24 performing evaluations. I designed a ran series of control experiments to measure how Open vSwitch affects systems resources and what level of performance it delivers in terms of throughput, latency, and scalability. Let us start with the resource monitoring. So here you go. Okay, so for resource monitoring, I selected four tools. Start from the system package of package for detailed CPU and memory statics at 1 second intervals. Each top for real-time visual overview of process resource consumptions. If top for monitoring network bandwidth per interface, and the free command for memory and the swap illustrations. I first took a Vaseline and Vaseline measurement. First I took a baseline measurement with OVS installed and running, but no network traffic falling. Now this is the ideal state. The results are very low resources consumptions. CPU was 98.43% idle, and meaning OBS used less than 2% of CPU at rest. The two demons, OBS V switched and OBS the B server, appear has two background process with the negligible negligible with a process with a negligible CPU time. Memory uses was 268 megabytes by out of the 1.96 gigabytes available. Again, a modest footprint. Network activity on the OVS bridge was zero and as expected. This baseline these baseline figures are important because they give us a reference point to compare against when the traffic is falling. So with a perf running and saturating the obvious bridge, I took measurement again to compare with the baseline. The CPU ideal percentage dropped from 98.43% to 79.1%. 79.1% because which means obvious consumed and consumed an additional 19.4% of CPU capacity under full loaded. This is because the user face daemon and the kernel datapad are both active. The kernel is forwarding millions of packets per second, which require CPU cycle memory use increased only marginally to around 285 megabytes, essentially stable. OBS does not dynamically allocated large amount of memory on the load, confirming it has a predictable memory footprint, and network activity graphs confirms traffic was falling across the virtual interface. The if TOF tool showed the bandwidth on the web interfaces, which are the physical ports through which traffic enters and exits the OVS bridge. Critically, the CPU overhead of roughly 21% is modest, considering that the switch was handling over 90 gigabytes per second of traffic. This demonstrates the OVS kernel datapad is highly efficient. The first path in the kernel avoids expensive context switches between user space and the kernel space for every packet. So yeah, in the next one under for performance evaluation I used Interperf 3, standard network performance testing tool. I ran Interperf 3 server inside the namespace 2 and the client inside the namespace 2 and the client inside namespace 1. So like I ran in iperf server inside namespace 2 and the client inside namespace 1, so all traffic passed through the obvious bridge. And I ran three different experiments: a single stream for 30 seconds and a single stream for 60 seconds to check for consistency, and four parallel systems for 60 seconds to access multi-core utilizations. The results were impressive. A single stream for 30 seconds achieved 64.4 gigabytes per second, and longer 60 seconds test with one stream got 70.3 gigabytes per second. And the suggestions the systems reaches peak performance once initial buffer are warmed up. For parallel systems streams pushed the throttle to the 93.3 gigabytes per second. These very high figures are expected in the virtualized setup because the traffic path is entirely within the same physical machine. Both namespaces are on the same host, so traffic goes through obvious but never hits a physical network card or a cable. In a real multi-host deployment, the throughput would be limited by the physical network link speed, typically 1 to 100 gigabytes per second. So but within a single host OVS kernel data path and can sustain this very high bandwidth, confirming the efficiency of the design. So for latency, I sent a 100 ICMP ping packet from the namespace 1 through the namespace 2, passing through the OVS bridge. The results showed excellent latency, a minimum of 0.016 milliseconds, and an average of 0.036 milliseconds, and maximum of 0.190 milliseconds with zero packet loss. These sub milliseconds figures confirm that OVS introduced very little forwarding delay for small packets. In a physical network, you would expect me 1 to 5 milliseconds just from cable, and switch propagations delay also obvious in this scenario is performing extremely well. So for its scalability, I tested how performance changed with 4 parallel IPARF3 streams. The scalability graph on the right shows throughout increasing significantly from 64 gigabytes per second with one stream to 93 gigabytes per second with 4. This is because OBS can distribute packet processing across multiple CPU cores. With one stream, a single CPU core handles all the processing. With 4 streams, the workload spreads across both virtual CPUs in BM. In a production environment with the more CPU cores, this scaling behavior would continue, making obvious a practical solution for high performance virtual networking environments. So to summarize the key findings, Open vSwitch 3.5.0 was successfully installed and configured from scratch on Debian 13 running in a VirtualBox, the VirtualBox network I built, with 2 Linux namespace connected through an obvious bridge, achieved 0% packet loss and sub-millisecond latency in performance testing throughout, peaked at 93.3 gigabytes per second using 4 parallel IPERF systems streams, demonstrating the efficiency of OBS kernel data path. The CPU overhead was modest, about 21% under full loaded compared to a less than 2% at rest. Memory usage was stable throughout at around 285 megabytes for future work and recommendations. The most meaningful next step would be integrate an open flow controller like a RYU on or ONOS, which would unlock obvious full software defined networking capabilities and allow dynamic flow rule management. Testing on a type 1 hypervisor such as KVM or Proxmox would remove the Windows host overhead and give more accurate measurements, and extending the multiple node setup to physical machines with the real network interface cards would reflect real world deployment conditions much more closely. Overall, one vSwitch, Open vSwitch provided to be a lightweight, highly capable virtual switch that is well suited for productions visualized environments, and this project has given me a practical experience with the core concepts of operating system visualizations and software defined networking. Thank you. So here are the references cited in this report and presentation listed in a Harvard format. The two mandatory sources from the brief are the official OpenBSwitch documentations and the virtual box documentations. I have also cited the original OBS research paper from a USNX NSDI 2025. Tenenbaum's Modern Operating Systems Textbook, and the two recent academic sources from 2022 and 2023 that cover SDN and performance analysis in virtualized environments. All web sources were accessed between March 20 to 25, 2026. Full reference details are provided in the written report. So that is my presentation. So thank you so much.